2 weeks ago, so we're still behind a little bit. And today we will try as much as possible to catch up, but then I think we will still try to focus more on chapter 3, and then chapter 2, I think Professor is like going through that. It is basically the fundamentals, and then we had like one assignment in chapter 3, so we're probably going to have one more. So right now, we will focus on the parts or the problems that we did not cover in chapter 3. We'll try to go through those today, and then hopefully when we finish on time, then we can have more assignments. So before we continue, I think during the first tutorial, tutorial 1, okay, during the tutorial 1, we had something like this, where we can determine the carrying capacity of our foundations, right? And then someone asked, I don't know who it was, I cannot really remember, that by increasing the depth of the foundation, df, does that mean this value will always get bigger? And I said, not necessarily. You may want to think, why not necessarily? Because here, if you make it deeper, these values all stay the same. I mean, this value, Q, will always increase, right? If you increase the df, the depth of the foundation. But that is if you are only considering the fact that the soil layer is uniform. You have only one type of soil. So it's like all the problems we are dealing with only one layer of soil, right? So if you increase the depth of the foundation, obviously this will go up. This stays the same, this stays the same. So that means this value will also go up.
There we have the equation for a square foundation and circular foundation.
Yeah.
Yes. And then for the first one is a strip foundation.
Yeah.
But I didn't see any case in which we use that equation.
Which equation?
The one for the strip foundation.
Oh, for strip footing? Probably because the questions you guys have did not like include the strip footings, right? But usually like it depends on the question you have at hand. So you can use any one of them. It depends on the question.
Yeah.
So if, yeah.
It's either a square or a circular. Then a strip foundation, how would it be? How is it?
You mean the
How is the strip foundation?
the shape?
The shape.
Oh, the shape. Okay. So in a strip foundation, usually it's like the length compared to the width. Like the length is very long and the width is very small.
So
There's
so this equation also works for rectangles, right?
Not necessarily, because I think there's a value, right? What's the value? B over L should be equal to a specific value. Then you can say it is a strip footing. I cannot exactly remember. Yeah, but the B over L should be equal to or greater than a certain value. Then you can say it is a strip foundation. Yeah. So usually when you say strip foundation, it means the length here is like very long, and this one is like very long and very small. So the comparison. So that is a strip. Yeah. So it's like, but usually the question will also specify whether you are dealing with the strip or the square or the circular foundation. But even if you don't have that, and then you feel like maybe here is 10 and here is like 1. So if you want to know, then you can. There's a specific value. L over B, if it is greater than a certain value, then you can say it is a strip foundation. Yeah, I cannot remember exactly off my head how much that value is, but yeah, there is. Okay, so what I was trying to say earlier is like, okay, so for example, this is our here, right? We get this. Okay, so we say here to here is like the depth of the foundation, right? So if we keep increasing this goes down, okay? That means df goes up. Then we say this QU will go up, right? That means the soil here is what? Is uniform, the same type of soil. Okay, it's the same, but let's assume now, okay, our foundation is, okay, it goes all the way down here. We make it deeper. Okay, this is our DF. The foundation is much deeper, but we have 2 layers of soil. For example, this is soil 1. This is soil 2, right? Usually when you deal with problems related to geotechnical problems, especially soils, you will not easily find only one layer of soil. It will be mixed. You have different layers of soils. So you have soil 1 and soil 2, right? So let's say this one is like, this is sand, okay, very strong. Sand, and then this is a weak layer. This is a weak layer, right? So maybe the phi here is higher, okay? But your DF, you go down. Your phi here is much smaller in this layer. It can be like, because this is a weak layer, you assume it's a weak layer, and this one is stronger. But the phi here is smaller. So if phi is smaller, and then maybe let's assume our C also is smaller. So you get the phi from there, MC value is smaller. This will be bigger, but this also will be smaller. This and this can be smaller, and then this may be bigger. So it's not always the case that if you go deeper, this value will be bigger. It depends on the soil condition you have. So it can go up or down depending on the soil condition. Okay? So if this soil here, like the one at the bottom, is stronger, obviously this value will go up. But if it is weaker, there's a chance that this value, instead of going up, it will go down. Because only one value goes up, but this and this have the potential to go down. Yeah.
How do we apply these formulas in case that we have different layers? We add the Euclid weight or
Yeah. Because the only problem will be, you may be thinking the only problem here is to find the Q, right? How do you find the Q here? Q you said is gamma multiplied by df, right? So let's say the soil 1, gamma is what? Gamma 1. Soil 2, gamma is what? Gamma 2, right? So how do you find the Q? Q equal to gamma 1 multiplied by the depth from here to here, right?
Yes.
Okay, so let's say d1 plus gamma 2 multiplied by d2. So you can easily find the Q. Okay? But you may be asking, then how do I know what is this and this? Right? So that depends on the interaction of this with the soil. Okay? The foundation here. So you will consider this value and not this one. You consider the one at the bottom, the base. Okay? So that's why I say it's not necessarily that if you increase the depth of your foundation, this value will always go up. So you have to see the soil condition. It's very important.
And what about the cohesion with 2 different layers? It would be different or
You mean that?
the cohesion?
The cohesion. Okay, so you will consider here where the foundation is located, the footing, on which layer, okay? So because we have considered the interaction between this, the footing base, and then the soil layer. So you consider this. So this, the values, that is the C and the phi will be from here. So if this is weak, then this value will get smaller. So this gets smaller, this gets smaller, okay? So you just consider this like. But most of the time, the problems we deal with in class are like, they will give us only single layers of soil. If it is more complicated, like you have multiple layers, you probably will use a software to do the analysis, make it easy. Okay, so let's try to catch up with the other parts that we did not do yet. So first we will try to do the eccentrically loaded foundations. So initially the problems we are dealing with is like the foundation is on the centric loading. So when we say centric loading, what that means is like, if this is your footing here, it's like this, okay? So maybe you have something like this, right? So the loading is like here, okay? Maybe you have your loading here, okay? But this is not always the case, okay? This is like very simple, very basic, so it's the centric. In some cases, not only will you have the Q, but you will also have a moment here, M. Okay, so you have a moment here. And then now you will have to modify the Q. Okay, so if you modify the Q, the location of this Q will not be at the center anymore. It may move from the center. So for example, it may be something like this. Our Q may move to somewhere around here. Okay? This may be our Q. And then this is the center of our foundation. So it moved away from the center. There's a space here. Okay? But when we are dealing with the center like this, if it is the center, the loading is at the center, we will assume that the distribution here is uniform, right? Like we will assume it's like this. The pressure is uniform because the loading is at the center of the foundation. But in most cases, when we deal with foundation problems, like it's not the case, like we say, like Q may move here. So the distribution will not be uniform. So it may be uneven in shape. So for example, they give us different conditions here, right? They say, in several instances, as with the base of a retaining wall, foundations are subjected to the moments in addition to the vertical load. So not only will you have the loading, but you will also have a moment acting on the base of the foundation. Okay, and then they have different conditions, okay? So here, condition one, they say when E, so E is the eccentricity. E means the distance. Okay, for example, we have this, so here, okay, goes here, and here, okay? So this is the center, okay? But our Q is maybe located here. Q, okay? So the distance from here to here will be our eccentricity, is the E. Okay, the distance, this loading, the modified loading have with the center of the foundation, okay? This is the center, so here is E, the eccentricity. So it says if this value is less than B over 6, what is B? B is the width of our foundation, right? So it's, for example, we have here, this is our B. Okay, if this value is less than B over 6, then the distribution of the pressure underneath the foundation will look like this. Okay, it may look like this. And if this value is equal to B over 6, it will look like this. At this point, this will be 0. You may want to ask yourself, why is it 0 at this point? How do we know it's 0 at this point when E equal to B over 6? So for example, we have something like this, right? We know that if the loading is not uniform, like you do something like this, it's going to be triangular in nature, right? For example, the maximum will be 1/3 from here, right? Let's say this is X, 1/3 of X. Here you will have your maximum loading. And the minimum value will be here. This will be 2/3 of X, right? This point will be 0, and then this one will have the maximum. So here we already say this is 0. How do we know, like at this point here, this is 0? We say this from here to here, or let's say from here to here is B over 6. So you assume okay? This is B over 6, or we can say 1 over 6 of X. So if you subtract 1 over 6 from X, okay? 1 over 6 of X here, 1/6 of X, you subtract that from here, which is so here will be 1/3 of x minus 1/6 of x. Okay, so you will know like the distance from here to here is 2/3. The distance from here to here is 1/3, and then this is 1/6, 1/3 minus 1/6. So we get this distance. So if you move here by 2/3 of x, by the time you get here, like this is going here. Okay, so that's why when this e over b, here to here we get 2/3 of x. When this is 1 or b/6, and this is 1/3 of x, and then you add that to this part, then this m here will become 0. So obviously we know that at this point this is 0. And then this one is a little bit more complicated because it's not here, and then it's also not here, but we know that from here to here will be 2/3 of x. Okay, 2/3 the value, and then multiply by, 1/3 here, and then 2/3 here. 1/3 to the bigger side, and then 2/3 to the smaller side. Okay, so here we have a few equations that we can use. Okay, so it says QB max. So okay, so we have this. So here is the maximum. Okay, the maximum loading is here, and the minimum loading is here. So if this is QB max, then this we know this end will be our maximum loading, and then here will be the minimum. Okay, so this is case 1, and then this is the equation we will use. So it's like 1 plus 6 multiplied by eccentricity plus b. So if you want to calculate the minimum, you just change this sign to minus. And then for our case 2, that is when e over b equal to 6. So we already know at this point this is 0, right? The q minimum. So we don't need to calculate this anymore, right? So we only substitute if you substitute e over b equal to 6 in this equation, then you will get this. If you try to do that, you will get this value here. Okay, so that's how this one comes about. They just substitute e over b equal to b over 6 into the previous equation, so they get this. Okay, and then this is the third condition. When it's like the eccentricity is greater than b over 6, it's like very large. It's like you put the loading all the way to one side of the foundation and not in the middle. Okay, so also usually before you do your calculations, it is important to do the eccentricity check. You have to make sure that your foundation meets the requirement of the eccentricity check. How do we do the eccentricity check? So the first thing first that we want to do is like, the formula for eccentricity is very simple, right? E equal to m over q. So your m is the moment. M is the moment divided by Q. So Q is the loading on the foundation, right? So we get this M and Q. So we get our eccentricity. So like for long-term conditions, that is like when we are trying to consider the effective stress analysis, then this value should be more than 1/6 of the width of the foundation, right? It should not be more than 1/6. So it's like if we are trying to do the long-term condition, so it's like eccentricity should be less than or equal to 1/6 of b, right? So that's the effective stress. And then if we are trying to do the short-term condition, that is the total stress, right? Eccentricity should be 1/3 of b. It should be less than or equal to. So you can also use this to check whether the foundation meets the requirements, okay? If it is more than this, you may want to adjust. Okay, so next, once we finish that, we can try to determine the ultimate bearing capacity of our foundations, right? So you can see like everything here, nothing is new, right? All the same, all the same. The only difference here is the B prime, is the only thing that is new, right? And the reason why we have to modify the B prime because it's like, initially we use the B because the loading is throughout, it's like making contact with the whole base of the foundation, right? But now the loading is not centric, so it's like moving to all these specific areas of the foundation base, okay? So maybe this is our footing, something like this. Something like this, and then when we draw this, if it is uniform, we know it will be like this, right? Something like this, this, right? So in the B, we just use the B directly, no problem. But if it's not uniform, then we may have something like this. You will expect something like this, right? So the B, instead of being from here to here, is only from here to here. So we use this. Okay, we have to consider this value instead of this. So that's how this B prime comes about. So we are just trying to see the contact, okay, the area of contact between the foundation and the pressure underneath. And then they gave us like some equations on how to determine the effective width, effective length. I think you guys probably already understand this, and I guess the professor already explained this in detail. It's like, this is your straight footing, and now we consider only half of this, right? We only consider half. From here to here is E, that is our eccentricity, right? But if you say this is half, then here to here is what? B over 2. If the whole of this is B, so if you only consider half, is B over 2, right? Then here to here, B prime will be B over 2 minus E. And then if you want to consider the whole thing, then you have to say what? B, it's like, here to here is B. So half of that is B over 2, right? So we want to know, like, from here to here, only B prime, so that is minus E. But this is only one side, right? So if you want both sides, then you have to say, if you want, like, we want to make it double, you say another B over 2 minus E. So this is equal to B prime. So that's how this value comes about. Okay. That's how that value comes about. And the L, so we are only looking at eccentricity is along the width. So the L remains the same, it's not going to change. Right? So L prime equal to L. And then it says one way eccentricity in the L side. So now you are looking at eccentricity from the side of the length. So if you are looking at eccentricity from the side of the length, that means you are going to modify the length, right? If you modify the length, maybe it will be smaller than the width. But we know that the length is always bigger than width, right? Width should be smaller. So you just check if B prime is the minimum of the width, and then this is just like this. You replace B with L, right? So the minimum of these two will be your B prime, and the maximum, because should be the larger, right? Maximum is larger. The length is larger than the width. So you just check which one is larger. The larger of these two will be your length. You just substitute that. And then the same thing. Sometimes you want to check eccentricity in both directions, not only in the B or the L direction, but you want to check in both B and L. So it's the same. Just put that in there, just like that. That's how they all come about. Okay, so next, we have a very a simple problem trying to use the eccentricity to solve our this bearing capacity problem. So it says a rectangular footing is 3 meter by 4 meter in plan, situated on a dry sand stratum with an embedded depth of 1 meter. So the depth of the foundation is 1 meter. Given that the footing is subjected to a total vertical load of 500, so the loading on our footing is 500 kilonewton, and the moment is 100 kilonewton per meter in the transverse direction, so it's like this. On each base at the center line, the angle of friction, so we already get our angle of friction and the unit weight. So we are going to try to find our okay, so first thing first, what we need to do, because we already know our M, right? We know the moment, we know the Q. So we can easily find this E, right? Eccentricity is M over Q, so it's like 0.2. And the B over 6 is like, what is the B? Is the width of the foundation is already 3, right? So we say 3 over 6. Oh, that should be 2 over 3 is. But this value is already, okay, we see here, this is less than the B over 6. So if it is less than B over 6, what do we do? So we use this. Okay. So since the eccentricity here is less than, E is less than B over 6, so we're going to use this, right? QB max. We just use this function, and then QB min, we just use this function to find these two for the problem we are trying to solve. So that is just what we did here. We substitute these values into when E is less than B over 6, and then we get our QB max and then QB minimum. So once we do that, the next thing we want to do is like, we're trying to find a QU, right? So the QU, what we do is like, we use this same equation, right? And try to find our QU value. And then we have to remember, this B prime needs to change. So we can easily calculate the B prime, right? So we say B prime here is 3 minus, okay, we are trying to consider the eccentricity from this side. Where is it? Okay, so this side, right? B prime is your B minus 2 times the eccentricity. We already show you how that comes about. So our B prime here is 2.6. So once we know our B prime, we find the C value. We know the C value from the question. We know the phi value and the gamma value. They are already given, right? So we use this and then find these values, right, from the Meyerhof-Berring parameters table. Okay, so once we have that, then we just substitute and find out FC, FQ, sorry, FCS, FQS, F gamma S. So we say like the B prime will actually affect these 3 values, right? So when you try to calculate this, and this, now you use B prime and not B. Okay, because these are shape factors. They are affected by the shape of the footing, right? They are affected by the shape of the footing. So you have to change this and this to B prime. The rest, they are like, this one is a depth factor, depth and inclination. So this should not be affected by the shape, like the change in the shape, right? B like reducing. So this one depends on the depth. Maybe if the depth changes, then this will change. Or if the inclination changes, this will change. But this one depends on the shape. So we are changing the shape when we introduce B prime. So this, and this changes. So we do the same thing like the previous, like what we have been doing previously, right? So the only new thing is FCS, FQF, F gamma S, we make sure we replace our B with B prime. That's all we need to do. And once we do that, and then we know like the new values, then we just substitute in the equation. I think this part everyone is pretty familiar. You just substitute and then punch in the calculator, and then you can just get the answer, okay? Okay, so for this part, is there anything you don't understand this part? Yeah.
Yes, for eccentric loading, so we are going to use only Meyerhof equation.
Yeah, we are using the Meyerhof
Because
equation.
it will change.
Yeah. Just like the shape factors are changing and all of things, so we use the Meyerhof based on this. Anything else?
Yeah. How do we know that the eccentricity is either on the B side or the L side? I mean, in this problem, we assume, or I don't know, why do we assume the eccentricity is on the B side?
Sometimes it will give you the question usually like they'll specify. If they say it's in the transverse direction, so that means it's along the width. If they say in the longitudinal direction, along the length. Okay, so you have to put that in mind. If they're asking for the question specifies is like the loading or the moment is along the longitudinal direction, then eccentricity is along the line. But here they specify this transverse direction, so we know it's along the width. Okay, so that's why we use EB here. Anything else? Yeah, so for this part, actually, the procedure and everything is just pretty similar. If you understand like what you did previously, that's the typical math of bearing capacity problems, then you just need to put in mind some basic few things. Just make sure like when you're calculating, you substitute the B prime where you need to substitute the B prime. That is specifically for this part. The shape factors, you substitute the B prime instead of the B, or maybe the L prime instead of the L, if it is like in the longitudinal direction, right? So we may have to consider changing this to L prime instead of L. But here we are walking along the width line, so we only change. Yeah, but if it says in the longitudinal direction, then we will use L prime here, right? Okay, so those are just the things that you need to pay attention to when you are dealing with simplicity problems.
I have a question.
Yeah.
In which part do we use QB max and QB minimum? In the last line,
You mean?
that one.
Oh. So it's like, this one is just giving you an idea of the distribution of the loading at the base of the footing, okay, the distribution of the pressure. So it's like, so it's like this. We have this, right? And then we have this and this. So here, since we know in our question, E is less than B over 6, right? So we have something like this, E less than B over 6 when we calculate it, right? So we know the distribution of the pressure at the base of the footing will be like this. So we just want to have an idea. What is the maximum pressure here? Okay, so that's the QB max. And then what is the limit? Okay, so it just gives us an idea of the distribution of pressure under the base of the footing.
Okay, I just give comment for this. Not yet, we haven't touched it, but generally we care about maximum value. And maximum value application will be shown for the retaining wall. Okay, but that's a later chapter, so don't worry about it. Right now, just know how to work out.
Okay, thank you.
Okay, so yeah, for now, like the max and the minimum values, just take it as an idea of how the pressure is distributed underneath the footing. Okay, so before we move on, anything else here? All good? Yeah.
Yes. In case of the sand, it was wet or saturated, then the angle of friction would be 0, right?
Not necessarily, no.
And if it was clay, a saturated clay,
Yeah, like it should be like when you're doing a long time or something like that for clay, yeah. But for sand, not necessarily.
so you can see that the inclination factor there
Yeah.
for F gamma I, you have 1 minus beta
Yes.
over phi. And if phi is 0, that's an indetermination.
Oh, the inclination factor.
Yes, if the beta over 0,
Mm-hmm.
and then
So, did I?
Pero yo pensé que phi es menor a 10, pero esta fórmula no hace eso.
no, it's right, I got it.
You got it?
Yes, got it.
If
Okay.
0, we will only have first two. I mean NC and NQ, and then
F.
okay, just stop.
Wait, here.
It's line,
Okay.
last line.
But
I got it.
okay, if sorry, I'm old.
Can you see?
So, ECI. Okay. Okay, so this part we don't need to care about that because this N 0.5 phi gamma n gamma. This part is 0. Sorry, n gamma is 0. So it doesn't matter how it look like. This part disappear because n gamma is 0. Okay.
Okay, so if no more problem on this part, I think we can just quickly take a look at the settlement part. Okay. Okay, so here we'll just take a quick look at the different types of foundation settlements. So usually we will have like two types of settlement. You will have the immediate settlement. This occurs immediately after the construction. You will experience some sort of settlement. And the long-term settlement is like, it takes more time. Okay, it can be like 1 year, 2 years, 3 years. Okay, it's mostly more like has to do with consolidation. So usually consolidation takes a long period of time. It can even be 5 years or 10 years. Okay, so that's known as the long-term settlement. Okay, so for now we will focus on the immediate settlement. That's like the settlement that just take place immediately, like when you finish construction. Okay, because you are applying a loading to the soil, and the soil will behave like kind of like an elastic material. When you apply a force onto it, it will definitely compress, right? Or it will settle, like in order it will settle. So here we have an equation. So this is the equation you can easily use. So they say the settlement is like the integral from 0 to x. So 0 to x is like the thickness, okay? The thickness of the soil layer you are trying to deal with. And then we all know what is strain, right? So it's like you are integrating this with respect to 0 to x, strain along the z-axis. So the change, like the small changes from 0 to x. So they easily just substitute this with these values and then just get this. But then this is not what we will use because this is a lot of mathematics. Maybe if you are using a software to do the analysis, this is what happens behind or in the background in the software. But then if we are trying to use our hands to do the calculation, there are simplified techniques we can use to solve these problems. You don't need to do all these integrations and all that. Okay, so it just says here we just need to know, okay, this is our settlement. And this is the modulus of elasticity of our soil, right? And then H here is the thickness of the layer we are trying to deal with. And then the Poisson ratio of the soil, okay? So that's how it changes lateral to longitudinal, like when you apply a loading. Poisson ratio is just the ratio changing lateral to side and the changing the horizontal side. Okay, so we just, and then we know what is this. Okay, so that should not be a problem. So usually when we're trying to calculate, this is what we will use, right? This is very applicable. You can easily use this equation to try to find the immediate settlement that occurs in the soil underneath your foundation. So this, we say the settlement is equal to QB net. So that is the net bearing pressure. So the first thing you need to evaluate, you need to know your net bearing pressure. And then we will also know the Poisson ratio of our soil. Okay, different soils will have different types of Poisson ratio. And then here is the average modulus of elasticity of the soil under the foundation. So what's the soil underneath our foundation? We need to know the modulus of elasticity. That will tell us how much it will deform, right, when we apply the loading onto it. And then B prime is equal to B, the corner of the foundation. So if we are trying to consider settlement at the corners here, this B prime is B. But if we are trying to consider the settlement at the center, we easily say B prime equal to B over 2. Okay, so we have this equation. So we know how to get this. We know how to get this and this and this. But how do we get this and this? Like the I sub S and I sub F. So here we have like a lot of equations that you can use to like find these values. I mean, these are very little equations. I don't think anyone will ask you to remember this. You don't really need to. You just try to make sure you understand how they are applied to solve problems. Okay, so you can easily like, okay, IS is the shape factor, so you can calculate it like this, right? And then they tell us, okay, we know this, we know this. How do we calculate our F1? You calculate it using this. F2 can be calculated using this. Okay, we are like, okay, we know this, But how do we know our A0 and A1 and A2? Then you come here. Okay, so it's like a long process, very tedious. Okay, and then this one is a function that is I sub f is a function of this, and this. So you can easily look at the table to find this. Okay, it's a depth factor. It depends on the depth of the foundation. And then alpha is a factor that depends on the location on the foundation where the settlement is being calculated. So are you calculating the settlement you are calculating, is it at the center or at the corner? Okay, so alpha depends on that value. So you have to like know what the question is asking you to do. Does it want the settlement at the center, or you are trying to find the settlement at the corner? Then you can choose the right alpha value. Okay, so here it says if you are trying to calculate the settlement at the corner of the foundation, alpha is just 1, and then n and h can be calculated using this. But if you are trying to find, oh sorry, this is the corner, and then the center, alpha will be equal to 4 instead of 1, and then this also will change. So as I said earlier, just know like what condition you are working with, and then apply the right equations. And then here we already mentioned, right? This I sub f is a function of this, and this. So here they just made a table for us. Okay, so first thing first, we just know, okay, what is our Poisson ratio? Maybe we say it's 0.3. Okay, 0.3. Okay, so it can be any of this, right? Something like that. So you ask yourself, what is our df over b? You know, okay, maybe it's 0.2. So we can easily find our if. Okay, 0.2 is around here, but what is the b over l? Is it this, or this? So you try to find which one is it, and then you can easily get your I sub f value. So you just read the table in order, and then you can easily get the I sub f. So you don't need to do a lot of calculation like you did for the I sub x. This is like a little bit more flexible. Okay, so here we have one simple example. It says a rigid footing of 2 meters by 4 meters in plan is situated on a dry sand stratum. So it is on dry sand, okay? With a thickness of 6 meters. So the thickness of the dry sand is 6 meters. The embedded depth of the footing, so the footing is only 1 meter in the ground, okay? Given that the average modulus of elasticity is 8,000, so we know our modulus of elasticity, and the Poisson's ratio is 0.3, calculate the immediate settlement under the net bearing pressure. So we are just trying to calculate the immediate settlement, right? Not the long term. So we already have this equation, so we just use this equation, okay? And then we are, for the center of the footing, okay, we are considering the center. So what is alpha? We know our alpha value is 4, right? So we have also know what is m. When you are considering the center of the footing, m is this, n is this, okay? So we use this, and then we just find these values, f1 and f2. Just substitute in those previous equations. Where are they? Okay, you just substitute in these equations to find these values. Okay, so once we know those values, we can find the I sub s. So the I sub s, it also, okay, this is how we calculate it, right? Here. So we already know this and this. And this one is already given, so we only substitute and then find the I sub s. Okay, so we know our b over l is 0.5, b over b is 0.5. What do? We go back to this table and then find the I sub f. So we get that value here, right? Because it's in between two values, it's not like exact. So it's in between two values. That's these two, okay? These two values. So we just say this plus this divided by 2. We try to find a reasonable range, something in the middle, okay? Because we don't know the exact value, so we just find the average of those two. So once you know that, what do you do next? You just substitute all the parameters into this equation. So that is this equation here. Okay, QB net, where is that? Okay, so in the question we already know QB net is 160, right? And then we know this value too. The alpha value is 4 because it is at the center of the foundation, right? And then what is the B prime? The B prime will be 2/2 for our problem, okay? So we just substitute and then we will get the immediate that's the flexible settlement. So it's like we have something like 13.42. So you just make sure like during the process, you get the right parameters. Are you working with the center? Are you working with the corner? Get the right equations and then just substitute here, then you can easily get your answer, okay? So when you get the flexible, like this is here, is the value for the flexible footing, right? If it is flexible, so this is the settlement. So there's a correlation between these two. So the rigid footing, like if it is rigid, the settlement is approximately 0.93 of the flexible, okay? So you don't need to go through the whole process to calculate the gain. You just multiply this value by this to give you an idea or a rough estimate of this, okay? The rigid. Okay, I think this question is quite straightforward. I mean, is there any complications? Anything you don't understand there? Pretty straightforward, right? Okay. Okay, good. It's already time, so I guess we take a break here for now. Okay.
Thank you.
Thank you.